Good morning. So this video is to complete the grade 12 November 2018 paper 1. I started with question 1 to 3 in the previous video, and this video will include questions 4 to 11. Okay, so let's get started. Question 4 says, initially a girl on roller skates is at rest on a smooth horizontal pavement. The girl throws a parcel of mass 8 kilograms horizontally to the right at a speed of 4 meters per second. Immediately after the parcel has been thrown, the girl roller skate combination moves at a speed of 0.6 meters per second. Ignore the effects of friction and rotation. Okay, so the first word that I'd like to point out here is the word smooth. The word smooth insinuates that there is no friction and that you don't have to take friction into consideration. Okay? So we start with question 4.1, and it says, define the term momentum in words. Okay, once again, I'm just going to reiterate, there is a document for grade 12s that has got all of the definitions on it. The definitions that will be accepted and marked correctly at the end of the year. You need to go and find this document online, or you need to ask your teacher for it, and you need to study those definitions off by heart because they won't accept just a general definition. Okay? But according to the memo, the definition for momentum is the product of mass, of the mass of an object and its velocity. So momentum is the product of the mass of an object and its velocity. Okay, question 4.2. Will the girl roller skate combination move to the right or to the left after the parcel is thrown? Name the law in physics that can be used to explain your choice of direction. Okay, so she's stationary. She's not moving anywhere, they say, to start with. But she has an 8-kilogram package in her hand, and they say that the girl throws this package to the right. So you see over here, she's throwing the parcel to the right, and she's throwing it with a speed of 4 meters per second. Okay, now the answer to this question is the girl will move to the left. Okay, and the reason for this is Newton's third law. Newton's third law is an action-reaction pair law. So it says that if object A, so let's say, for example, you've got a wall and you're standing at the wall and you're pushing against this wall, okay? Newton's third law says that if you are exerting, you as in object A and the wall as in object B, if object A or you exerts a force of, let's say, 20 newtons onto object B, then object B exerts a force of equal magnitude but in the opposite direction onto object A. And this is Newton's third law. It's a action-reaction pair. So it's saying that for every force, there is a counteracting force. For every force that object A exerts on object B also exerts a force of equal magnitude but in the opposite direction on object A. So because she is exerting a force on this parcel and throwing it and pushing it to the right, it means that when she exerts the force on the parcel exerts a force of equal magnitude but in the opposite direction on her. Okay? So she will move to the left. She will move to in the opposite direction that she threw the parcel. Okay? This concept is also considered to be a principle of conservation of linear momentum. Okay, so now we move on to question. The next thing says that the total mass of her roller skates is 2 kilograms. So her roller skates weigh about 2 kilograms. Okay, And they want to know in question 4.3, what is the mass of the girl? Okay, so we've already said that this is based on Newton's third law, and we've already said that this is basically covering the principle of conservation of linear momentum. So we know that we can use our conservation of linear momentum formula to calculate the mass of the girl. Okay? So let's have a look. I'm going to do this in black. And I'm going to start by writing out our conservation of linear momentum formula. So the formula says the sum of momentum of the system at the start, or initial momentum, P stands for momentum, I is initial, is equal to the sum of the momentum in the final scenario, or at the end of the scenario. Okay, and there's no friction, and no energy is said that they've said that no energy is lost or anything like that. So we can assume that conservation of linear momentum applies, as I've said. So now we go and we write out this formula. Okay, we're going to make let's say this is P, or let's say PA, parcel can be PA, and she can be GI. Okay, because remember, initially we need for both of them. So on this side of our formula, we need the momentum initially for the parcel and the girl. And on this side, we need the momentum for the parcel and the girl. So the overall kind of formula goes mass 1 times V1 plus mass 2 times V2. And this should actually say 1 initial and 2 initial. And that's equal to mass 1 times V1 final plus mass 2 times V2 final. Okay? So you need to either decide, is the girl going to be 1 or is the parcel going to be 1? Because this 1 is basically labeling object 1 and object 2. Okay, so from here, we can then substitute in the values that they have given us. Okay, so I'm going to make the girl object 1, and I'm going to make the parcel object 2. Okay, so they want the mass of the girl. I don't have the mass of the girl, okay? But the mass that I calculate will include the mass of the girl and the roller skates. And they told us that the roller skates are 2 kilograms. So for the mass of the girl, I'm going to substitute in m of the girl plus 2, because that gives me m1. It gives me the total mass of the girl plus the mass of the roller skates. Okay, so at the end, I'm going to take whatever I get for m1 and subtract 2 to give me the mass of the girl. I don't want the total mass. I don't want the mass of her and the roller skates. I just want her. So that's why I've substituted in mass of the girl plus 2 here. So that at the end, we can account for this 2 kilograms that we don't want to be included in her total mass. Okay, so we go like that. And then we multiply our mass of the entire girl roller skate system by 0, because their initial velocity in the scenario was 0. She wasn't moving. It said initially a girl on roller skates is at rest. So that means her initial velocity was 0. Okay, perfect. Then we say plus mass number 2. Mass number 2 was the parcel. So we say 8 kilograms. And we also multiply that by 0, because it says initially a girl on roller skates is at rest on a smooth horizontal pavement. The girl throws a parcel. So if her initial velocity, she's holding the parcel. So if her initial velocity is 0 and she's holding the parcel, it means the initial velocity of the parcel is also 0. Okay? Now we go and we substitute in, I'm going to do it here at the bottom because I'm going to run out of space on the side here. So then the final ones. So again, we've got our M1 times VIF. So our M1 is, again, it's going to be mg plus 2, because that's going to be our mass of the girl plus the 2 of the roller skates, because we're considering them one thing at the moment. And we multiply that by her velocity after she throws the parcel. Okay, and it says here in the description, the girl roller skate combination. So you can see that's why I've included her mass and the 2 kilograms of the roller skates into my calculation, because it's the girl roller skate combination. Okay, so we multiply that by 0.6 meters per second. Okay, original direction of motion that's described is to the right, so we'll take to the right as positive and we'll take to the left as negative. It's very important that you stipulate which direction you're taking as positive in all of your questions. Okay, so here now what do? We say, okay, multiplied by negative 0.6 meters per second, because she was traveling to the left, so in the negative direction. So we're still here on the second half. And then we say plus mass 2, so the mass of the parcel, which is still 8 kilograms, multiplied by the velocity of the second one, which in the scenario says is 4 meters per second. And we can substitute that in as positive because it's to the right. The parcel is moving 4 meters per second to the right. Okay? So what we're left with basically is this entire right-hand side of the equation, or left-hand side of the equation, sorry, becomes 0, because anything times 0 is 0, anything times 0 is 0, and 0 plus 0 is 0. So we say 0 is equal to, and then we say mg plus 2 times negative 0.6 plus 8 times 4, that's 32. So we can take the 32 over, it becomes negative 32 is equal to negative 0.6 mg minus, because we're going to go negative 0.6 times 2, which gives us negative 1.2. So we take our calculator, we take this over, it becomes negative 32 plus 1.2, because remember, when we take a negative over to the other side, it becomes positive. So now we're left with negative 30.8, and we divide that by negative 0.6. And the mass of the girl is 51.33 kilograms. And that's your final answer. Okay. Now we select all of this. Hopefully that all made sense. Okay, now we have a look at our next question. Our next question says, calculate the magnitude of the impulse that the girl roller skate combination is experiencing while the parcel is being thrown. Okay, so our first important step is to know what our formula for impulse is. So this is now, we're doing 4.4. Our formula for impulse is change in momentum, which is otherwise known as mass times Vf minus Vi. Okay, so change in momentum. This formula can also be written as because you're calculating momentum at the end and you're subtracting it from momentum at the start. So now we can go and we can basically just substitute in. You've got all of the information, and they're looking specifically for the impulse on the girl roller skate combination. So what am I going to do? I'm going to take the mass of the girl roller skate combination, which is the 51.33 that we just calculated, plus the 2 of the roller skates, because they don't just want the one of the girl, they want of the girl roller skate combination. So you need to take the mass of both into consideration. Okay, I actually just want to move this. I'm running out of space here. So we say change in momentum is equal to mass times Vf minus mass times Vi. So there we're going to say 51.33, because like I said, that's the mass of the girl plus the mass of the roller skates. Remember, it can also be written like this, mass times Vf minus Vi. That's how I'm going to do it. It's just easier for me to write it like that. But it's the same thing. It's exactly the same thing. All that you've done here is multiplied the mass into the bracket. So it's going to be mass, which is the girl's mass, 51.33, plus the mass of the roller skates, multiplied by your final velocity, which was negative 0.6. Because remember here it said that after she throws the parcel, she travels at 0.6 meters per second to the left, and we're taking to the right as positive. So it means we have to make it a negative, and we subtract that from the initial velocity, which we already know was 0 because it said initially she's not moving, she's stationary. Okay, and so now you plug that into your calculator. You say 51.33 plus 2 equals, and you multiply your answer by negative 0.6. And that answer gives us, so our change in momentum or our impulse is equal to negative 31,998 newtons, which is negative 32 newtons about, because we're rounding off, right? Okay, so that's the magnitude of our impulse. And just remember also, I think I got the just remember you need to focus on your units. So let me just fix this unit here quickly. I'll say equals negative 32, and impulse is measured in newtons per second. Sorry, not newtons, but newtons per second. Okay. Very important that you get your units correct. Okay. Then the last question says, without any further calculations, write down the change in momentum experienced by the parcel while it is being thrown. Okay. So remember, we just said that impulse is the same as change in momentum. So they're totally trying to throw you off here by asking you to calculate the magnitude of the impulse in the first question, and then by asking you to calculate the change in momentum in the second one. Essentially, they're asking for the exact same thing. Okay? And as discussed in the beginning, Newton's third law applies here, an action-reaction pair. So this 32 newtons per second that you've calculated for the girl and the roller skates combination, okay, another unit for which is known as kilograms per meter per second, okay, is the exact same magnitude of the change in momentum or impulse of the parcel, but it's going to be in the opposite direction. So it's not going to be negative. Okay? So your answer, no additional calculations are needed here as they've stipulated. And you know that change in momentum is the same as impulse. So the only thing you really have to change from the answer that you calculated in 4.4 is the the sign, which indicates direction. Okay? Because the direction of this impulse or change in momentum for the girl roller skate combination was 32 newtons per second to the left. But for the parcel, it's going to be exactly the same, but it's going to be positive because it's going to be moving in the opposite direction. Okay, perfect. Now we move on to the next question. Question 5. So, the diagram below is not drawn to scale and it shows a vehicle with a mass of 1,500 kilograms starting from rest at point A at the bottom of a rough incline. Okay? Whenever you see the word rough, it means that friction is there. There is friction. Okay? Smooth means no friction. Rough means yes, there is friction. Okay? It says point B is 200 meters vertically above the horizontal. The total work done by force F that moves the vehicle from point A to point B in 90 seconds is 4.80 times 10 to the power of 6 joules. Okay, so the first question says, define the term non-conservative force. Okay, again, just reiterating, you need to find your definitions and you need to learn them. But I'll tell you what this one is. On the memo, they have the official definition as a force is non-conservative if the work it does on an object which is moving between 2 points depends on the path taken. Okay, so there's just something very important that I want to spend some time summarizing here quickly. So, a non-conservative force, okay, it is dependent or depends on the path taken. So the path taken matters, okay? And examples of forces that fall under this category are friction, air resistance, tension, and any type of applied force. Okay? And then just kind of the same idea, but for conservative, it's independent of the path taken. So the path it takes has absolutely zero effect. Examples of conservative forces include gravity, elastic spring force, electrostatic force, and magnetic force. So I just wanted to make a little summary of non-conservative versus conservative, just so that you've seen it and it's not too confusing once you get into your exam, okay? Okay, so now they say, is force F a conservative force? Choose from yes or no. And they've just said that the total work done by force F, which moves the vehicle from point A to point B in 90 seconds, is 4.80 times 10 to the power of 6 joules. So basically, force F is an applied force. It is some kind of motor or applied force that is getting this vehicle, this 1,500 kilogram vehicle, to move from point A to point B. It's a type of applied force. Okay, and the question is force F a conservative force? Okay, so your answer is no. Force F is not a conservative force. It is an applied force which falls into our non-conservative force category. Okay, now we move on to question 5.3. Calculate the average power generated by force F. So my suggestion to you guys is you need to tear your formula sheet. There's always a formula sheet at the back of your paper. You need to tear your formula sheet off of the back of your paper and you need to have it sitting next to you throughout the whole exam. Okay, it's just better for your brain to be able to immediately see the formulas. Whenever you see questions like this, you need to go to your question, you need to see what information have they given me and what are they asking me to calculate. And what you need to do then is to your you go to your formula sheet and you see which formula has all of the information in it that I have and which formula has the variable in it that I'm hoping to calculate. Okay, so very important. Don't try and guess these formulas out of your head. So we know that a formula, they're asking for the power generated by force F, okay? They've given us work done and they've given us time. And on your formula sheet, you will see that there is a formula that goes power is equal to work over change in time. So you can see this question is only for 3 marks, so it's not going to be particularly difficult. So you're going to substitute in your work value, which is 4.80 times 10 to the power of 6 joules, over your change in time, and you know your SI unit for time in physics is seconds, so you don't have to do any conversions with the 90 seconds they've given you. You just plug that in, and then we plug that into our calculator. So we say 4.80 times 10 to the power of 6 over 90. And that gives us a value of 5, 3, 53,333.33, and our unit is watts. The unit for power is watts, so we put a W there. Okay, and that's question 5.3. Now we move on to 5.4. So it says the speed of the vehicle when it reaches point B is 25 meters per second. Okay, 5.4 says state the work energy theorem in words. So before we get onto that, I just want to get rid of this. Okay, so 5.4, what is the work energy theorem? The work energy theorem states that the net or total work done on an object is equal to the change in the object's kinetic energy. Okay, the net or total work done on an object is equal to the change in the object's kinetic energy. Okay, like I said, these you have to be studying off by heart, okay? And then 5.5, the final question in this section. It says, use energy principles to calculate the total work done on the vehicle by the frictional forces. Okay, when they tell you to use energy principles and they put it in bold like that, sometimes these questions, there's multiple ways that you can calculate it. You can use a variety of different formulas and you'll still get to the same answer. And one of the sets of formulas that usually still works in these questions is your equations of motion. So they're specifically telling you in question 5.5 that you're not allowed to use equations of motion. They want you to specifically use your work formulas. Okay, so just be careful because you'll get 0 if you use anything other than your energy principles, and your energy principles are your work formulas. Okay, so let's have a look. For this section, we are going to be calculating the total work done by frictional forces. Okay, so the formula we use here is the net work done is equal to change in kinetic energy. Okay, and the reason we consider frictional forces to be synonymous with net work done is because it's the frictional force that's actually slowing this 1,500 kilogram block down. So remember, the net force is when we take all of the forces into consideration, all of the work into consideration, what net work is being done? What is the overall outcome at the end of all of the forces and the works being applied, okay? And it is usually our frictional force that we can take into consideration when we're looking at net work. So our net work formula now becomes an accumulation of all of the work that's being done on this object. So we're going to change work net into the work done by weight plus the work done by friction plus the work done by our force F. Okay? Because when we draw our free body diagram of our object, we've got normal force because it's on a horizontal surface. We've got weight. We've got F applied, or the F force that they've indicated here. Okay? And we've got friction. Okay? Obviously, some of these will have to be, it'll look a little bit different when the object is actually on the slope. Okay, but very important to remember is that weight plays a very important role when an object is on an incline. So when an object is on an incline, you're very often going to have to find yourself calculating your components for weight. So you're going to have to calculate a horizontal component for weight, Wx. Okay. Anyway, and then we just get rid of this, it's in our way. Okay, and we say equals our change in kinetic energy is going to be half mvf squared minus half mvi squared. Okay, so we basically just expanded on this formula, and I've just explained to you how I got work done by weight plus work done by friction plus work done by force F. Okay, so now we go and we substitute all of these things into our formula. We are looking for the work done by friction. So this is what we're looking for. So we're not going to have anything to substitute in for work by friction because that's what we're trying to calculate. So what we're trying to substitute in now is everything else. So we go and we say, okay, well, how are we going to calculate the work done by weight when the object is on the slope? Like I said, here you're going to have to use your trigonometrical functions to calculate the to calculate the the horizontal component of x. Okay, so we do this by drawing our triangle. Okay, and you know that we're looking at weight. We're looking for the vertical component or the horizontal component of weight. So your weight is 1,500 kilograms. We want to convert that. This is a mass. We want to convert it to a weight. Weight is equal to mass times gravitational acceleration. So we say multiplied by 9.8, which means that our weight comes to 14,700 newtons. Okay. Then we know that we've got this value over here. So this is our 90-degree triangle. This is our 200, the value that they've given us there. Okay. And we know that our formula for work is equal to force times change in x cos theta. Okay, calculated the force value. It's going to be the 1,500 times 9.8, which is our 14,700. So we say, carrying this formula on here, we say 14,700 multiplied by change in x. Okay, so they've given you the change in x as a vertical height, not a horizontal height, but it's fine. It will still work because remember, essentially this little cart is starting at the bottom and ending at the top. So they're giving us a vertical change in x. And we say times cos theta. And this is basically the angle between your direction of motion and your displacement. Okay. And here we substitute in cos 180 degrees. Okay. And that's what we substitute in for the work done by weight. Okay. And the reason this is 180 degrees is because weight goes down, but the object itself is traveling up. It says that it's traveling a vertical distance of 200 meters. Okay. And so they're going in opposite directions, which means the angle between them is 180 degrees. Okay, so I'm just going to get rid of all of this because this might be confusing some people. So I'm basically just I've tried to explain now where I've gotten all of my values from. Now I'm just going to substitute them into the formula. Okay, so as I said, for the work done by weight, it's going to be the force multiplied by change in x multiplied by cos theta, because that's our formula for work. Okay, and we have all of these values. plus the work done by friction, which is what we're looking for, so we substitute in nothing, plus the work done by force F, which they already gave us. That was 4.8 times 10 to the 6. So we substitute in 4.80 times 10 to the power of 6. Okay? Dot, 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 dot. Obviously, I'm running out of space here. So let's quickly plug in these values. So this one's going to be, as I said, 14,700 multiplied by 200 multiplied by cos 180 degrees plus the work done by friction plus our 4.80 times 10 to the power of 6. So this that I've just written out here is the left-hand side of my equation. Okay? So I'm going to plug that into the calculator so that I can get a working value. So that gives me a working value of negative 294 plus the work done by friction plus 4.8 times 10 to the power of 6. Remember, this is just the left-hand side of the equation. Okay? Now we can add those together. So negative 294,0000, and we say plus 4.8 times 10 to the power of 6 gives us a value of 186. Okay, plus work done by friction. So that's the left-hand side of our equation. And we say equals to half, because now we're doing the change in EK section. So it's going to be half. Our mass is going to be 1,500. Okay. And remember, this can be changed to half mass times VF squared minus VI squared. Remember, you can simplify it. I might be confusing you a little here. So we substituted in our half times our mass, and now we substitute in our VF minus our VI squared. So they tell you that the final velocity is 25 meters per second, and it tells you that the vehicle starts from rest, so you know your VI is 0. So it's VF squared minus VI squared. And now you substitute all of that in, and you get a value for the work done by friction. And that comes out to be negative 1.39 times 10 to the power of 6 joules. And that's the work done by your frictional forces. Okay? So this is a bit all over the place. Like I said, I run out of space. But overall, this, if I delete the rest, you should be able to see So here's your formula. Your work net is equal to changing kinetic energy. So we figure out what are all the forces acting on this object, its weight, its friction, it's the applied force that we discussed, and that's equal to changing kinetic energy, the formula for which is half mvf squared minus half mvi squared, which can be simplified as half m times vf squared minus vi squared, just to make it easier. And it kind of goes from being this equation to this when you've plugged in all your information, and this is your final answer. Okay, cool. Now that's that question done. Let's move on to question 6. Okay, so question 6 is a Doppler effect question. Okay, let's have a look. It says the alarm of a vehicle parked next to a straight horizontal road goes off, emitting sound with a wavelength of 0.34 meters. A patrol car is moving at a constant speed on the same road. The driver of the patrol car hears a sound with a frequency of 50 hertz lower than the sound emitted by the alarm. Take the speed of sound in air as 340 meters per second. Okay, so number 1, state the Doppler effect in words. Okay, so the memo tells us that our Doppler effect in words goes as follows. The change in frequency or pitch of the sound detected by a listener, because the sound of the source and the listener have different velocities relative to the medium of propagation. I'm just going to read that one more time. The change in frequency or pitch of the sound detected by a listener, because the sound source and the listener have different velocities relative to the medium of sound propagation. Okay? Now, the next question says, is the patrol car driving towards or away from the parked vehicle? Give a reason for your answer. And this is where I've now brought the summary for us to look at. Okay, this is something else you need to study off by heart, okay? This is your Doppler effect formula. Okay, so frequency of the listener is equal to the velocity of sound through air plus the velocity of the listener over the velocity of sound through air plus the velocity of the source multiplied by the frequency of the source. Okay? And the issue is, as you can see here in the middle, it says plus or minus, plus or minus. And you need to be able to determine, are we saying velocity of sound through air plus the velocity of the listener, or velocity of sound through air minus the velocity of the listener? And the way we determine that is by knowing, is the source moving towards the listener? Is the source moving away from the listener? Is the listener moving towards the source? Or is the listener moving away from the source? This is a very important little summary. I would definitely suggest you write it down, okay? But it states here, it says that so it says the alarm of a vehicle parked next to a straight horizontal road goes off, emitting the sound with a wavelength of 0.3 meters. So the vehicle with the alarm going off is the source, okay? A patrol car is moving at a constant speed on the same road. The driver of the patrol car hears the sound with a frequency that is 50 hertz lower than the sound emitted by the alarm. Okay, so we've got a stationary source because our parked vehicle is our source, and we've got a moving listener. Okay, and here, so that means that when we've got a moving listener, we're looking at the bottom two. Okay, we're not looking at the top two because that's when the source is moving. But they've clearly indicated that the source is parked and staying still. So we're looking at the listener. Okay, and they've said that the frequency of the alarm that's being detected by the listener, so the policeman in the patrol car, is 50 hertz lower than the sound that is actually being emitted by the source, which is the parked vehicle. Okay? So if it's 50 hertz lower, it means that the listener must be moving away from the source because that's negative. If positive means that your ended value will be bigger than your actual frequency, okay? Negative value means that your final value will actually be smaller than the real value. And they're saying here that the sound that he's hearing is actually lower or smaller. So from our little summary, we can therefore determine that the listener is moving away from the source. Okay? So that's your answer to 6.2. Like I said, very important to just take note of this little summary. You won't be able to answer the Doppler effect questions if you don't know what's going on here. Okay? But basically, what it means is that for our question, we've determined that our listener is moving away from the source, which means that when we substitute in our values, we need to say V minus VL, not V plus VL. Okay? So 6.3, calculate the frequency of the sound emitted by the alarm. So you can tell that this is only for 3 marks. It's not going to be difficult, okay? So all you have to do here is you are looking for the frequency of the emitted sound. They've only given you the wavelength, okay? But converting wavelength to frequency is actually quite simple. What you do is you use the formula V is equal to frequency multiplied by wavelength, okay? And we're talking about the speed of sound in air. So V is the speed of sound in air. So we substitute in. If 340 meters per second is the speed of sound through air, and we're looking for a frequency, and the wavelength they gave us is 0.34 meters. Remember, the SI unit for wavelength is meters. So if they give it to you in something else, you need to convert it, okay? But they've given it to us in our SI unit. So we calculate that, and that means that our frequency ends up being 1,000 hertz. So this is the frequency of the source, okay? So the frequency of the alarm being emitted by the parked vehicle is 1,000 hertz. And it says that the patrol car driver hears a frequency that's 50 hertz lower, which means that he hears a frequency of 950 hertz. Okay? And because it's lower, you know that 340 minus 50 is going to give you a smaller number. So you know that the listener is moving away from the source. Okay, I hope I've done a good enough job of explaining that. Okay, the next question says that they want you to calculate the patrol car moves a distance of X meters in 10 seconds. Calculate distance X. Okay, so this one's a little bit more difficult. Okay, but the principles remain the same. We start with our Doppler effect formula, which is frequency of the listener is equal to the velocity of sound in air plus minus the velocity of the listener over the velocity of sound in air plus minus the velocity of the source multiplied by the frequency of the source. So this is frequency as observed by the listener. Okay, so now we see they are looking for the distance that the patrol car travels in 10 seconds. In order for us to get distance, we need speed, okay? Because remember, velocity is equal to change in x or displacement or distance over change in time, okay? We have time, we're looking for distance, so we need to calculate velocity. And we're trying to see how far the patrol car moves. And the patrol car, as we've already determined, is the listener. So we are looking for the velocity of the listen. So knowing this, we substitute in everything we know. As I already said to you, we determined that the frequency of the source was 1,000 hertz, and they tell us that the listener hears a frequency that is 50 hertz lower. So the frequency as observed by the listener is going to be 1,000 minus 50, because this is the frequency of the source, and he hears it 50 hertz lower. So this is the frequency as observed by the listener. Then we substitute in 340. We already know that it's a negative value. We're subtracting it. It's supposed to be smaller. Minus VL is what we're looking for. Divided by 340 again, which is the speed of sound through air. And our source isn't moving. Okay, it has no velocity. So we just say 340 plus 0. It's got no velocity, so 0. It's not really important. Multiplied by the frequency of the source, which we also calculated, which is 1,000. Okay? You substitute all of that in, you divide away, and what you get is the velocity of the listener was 17 meters per second. Okay? And like I said, now to get a distance, it's super easy because you already know what the formula of velocity is. Velocity is equal to the change in the distance or the displacement over time. So now we say V is equal to, or even you can even do it speed. Speed is equal to distance over time. Remember, speed and velocity are the same thing, except speed doesn't have direction. So as long as you're just substituting in the value, you'll be fine. Speed is equal to distance over time. So we say 17 meters per second is equal to the distance that we're looking for over 10 seconds, which means the distance he traveled was 170 meters. Okay, very basic principle, but still for quite a few marks, 6 marks. Okay. Now we move on. Give me a second, I can get rid of all this extra stuff. Okay, so our next question is electrostatics. Okay, let's have a look. Question 7. Question 7 says, 3 small identical metal spheres P, S, and T are on insulated stands, and they are initially neutral. Okay. They are then charged to carry charges of negative 15 times 10 to the negative 9 coulombs. Q is, so you don't know Q, and they've given you T. So you can see we've got metal spheres P, S, and T. So they're saying that the charge of P, originally all of them are neutral, then they add a charge of negative 15 times 10 to the negative 9 coulombs on P. They don't really tell you what they charge S to be, and then they tell you that they charge T to be 2 times 10 to the negative 9 coulombs. Okay? The charged spheres are brought together so that all 3 spheres touch each other at the same time and are then separated. The charge on each sphere after separation is -3 times 10 to the -9 coulombs. Determine the value of the charge on Q. Okay, so it's very important to remember that not all of your formulas that you're going to need are on your formula sheet. Okay? And one of the formulas, I'm not sure if it's there. I don't think that it is there. Okay? I don't think that this formula is there. But when they give you a scenario where they tell you that they've got spheres that were originally charged and then they bring them into contact and then they separate them and they want to know what the new charge is, that formula generally goes like this. It goes Q net. Usually you work with only two spheres. So maybe the formula looks more familiar to you as Q1 plus Q2 over 2. But it's actually over the number of charged objects you have. So this is what it usually looks like. Because usually in the scenario, they'll say, oh, we've got two spheres, we bring them into contact. What is the new charge? So then you substitute in the charge with the sign, with the negative or the positive into here. For the second one, you substitute into here, also with a sign, and you divide by 2, and that will be the new charge on both of them. Because what happens, charge is equally distributed between objects that come into contact with one another. Okay, so you just need to make a small adjustment to this formula because there's 3 spheres. So instead of having only 2, we're just going to add another one. And instead of dividing by 2, we're going to divide by 3 because now we have 3 charged objects. So like I said, be careful. Not all of your formulas are on your formula sheets. I think this is one of them. So we go now and we substitute in. We say the charge on P plus the charge on S plus the charge on T divided by 3. And we actually already know what Q net is because they tell us at the end Q net is equal to -3. So we're doing this calculation a little bit differently. So we go and we say, well, we know what Q net is at the end. It's -3 times 10 to the -9. Okay, also important point, remember that when they give you these values, you need to make sure that they're all in coulombs. Coulombs is our standard SI unit, okay? If they give it to you in something else, like nanocoulombs or kilocoulombs, anything like that, you need to convert to coulombs. Okay, but they've been nice to you here, so you don't have to worry. So we go -15 times 10 to the power of -9 plus Q plus 2 times 10 to the -9 divided by 3. And now you've got your equation and you solve for Q. Okay? And when you've solved for Q, you should get a charge of +4 times 10 to the -9 coulombs. Okay, hopefully that made sense. Okay. So let's have a look at the next question. The next question says, draw the electric field pattern associated with the charged spheres S and T after they are separated and are returned to their original positions. Okay, so after they've all come into contact with each other, they all have a charge of -3 times 10 to the -9. Because remember, charge is distributed evenly amongst or between objects that come into contact. Okay, so your charge at the end is -3 times 10 to the -9 on all of them. So the magnitude is not so important, it's the sign. Okay, and I've just put these here to kind of make it easier for you to see what's happening. So point charges, they can ask you to draw a point charge field pattern. And so this is a point charge field pattern. So you can see a positive charge has got electrostatic force moving outwards, and a negative point charge has got electrostatic force moving inwards. Okay, but when they ask you to draw a point charge diagram for S and T after they've been separated, it means that they're asking you to show that sphere S is repelling sphere T. And this is kind of what your diagram is going to look like. The only difference is your point charges are negative. They're not positive. So you're going to have negative, negative. And instead of your arrows going out like they are in this positive diagram, they're going to be going in towards the center. Because remember, S and T are going to be negative after they've been separated. And remember, like repels like, and opposites attract. So if both of them are negatively charged, they're going to be repelling one another. This diagram shows you attraction between a positive and a negative. This diagram shows you repulsion between a positive and a positive, a like and a like. So the negative for the repulsion diagram for a negative charge is identical to this. It's just the charge in the middle, you're not going to write positive, you're going to write negative. And all of these little arrows that are traveling outwards, you're going to change the direction to inwards, to towards the little dot, like here, instead of away from the dot. So this is the diagram pattern that you're going to be drawing. And the reason I've shown you all of these is because they can ask you to draw anyone. They can ask you to draw anyone, so you need to know all of them. Okay. So let's move on. Our next question says the spheres, each with a new charge of -3 times 10 to the -9, are now placed at points on the x-axis and the y-axis, as shown in the diagram below, with sphere P at the origin. So what they mean by that is when you have a Cartesian plane, remember a Cartesian plane is like x and y. This is your Cartesian plane, where you've got your y-axis, your x-axis. So this, they've just drawn the little corner. They've drawn this quadrant over here. And your origin, or the word that they're referring to here, is the point in the middle of your Cartesian plane. Obviously, it's at the side here because, like I said, they've only drawn this part of your Cartesian plane. So that's what they mean by the origin. It's the point at the center of your Cartesian plane. Okay. So the first question says, state Coulomb's law in words. Okay. So Coulomb's law says that the magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. One more time. The magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. So this is basically just a description of Coulomb's law formula, okay, which is what we're going to be using now in the next section of this question. Okay, so the first mathematical or calculation question says, calculate the magnitude of the net electrostatic force acting on sphere P. Okay, so obviously we've got a bit of a problem here because we've got P and T acting on the horizontal or x-axis, and we've got S and P acting on the vertical or the y-axis of our Cartesian plane. And we can't add forces up. We can't get a net force of forces that are not occurring in the same plane. Okay, we can only add and subtract forces that are moving in the same dimension. So they either need to be both horizontal or they need to both be vertical. But we do know how to calculate Pythagoras. We do know how to use Pythagoras. Okay, so when you get an electrostatic question like this, where you've got something acting on the x and on the y, you are going to use Pythagoras to calculate your net force. The same way we calculate the hypotenuse of a triangle. In this scenario, the hypotenuse of our triangle is going to be our net force, okay? And if you go back and recap some principles from grade 11 with forces, you'll understand why we're doing this. Okay, so what we start with is we say, well, what formula do I need? I need my Coulomb formula, my Coulomb's law formula, which goes as follows. Electrostatic force is equal to constant K multiplied by charge 1 times charge 2 over the distance between the charges, or over the square of the distance between the charges. Okay, and now we basically just use this formula to calculate our net electrostatic force between P and T, and our net electrostatic force between S and P. So I'm going to start with SP. Electrostatic force of SP, of charge S on P. So we start with K. K is a constant. You can get it on your formula sheet. And the value for it is 9 times 10 to the power of 9. Okay? Then we substitute in our charges. Remember, they want the magnitude. So we don't have to work with positives and negatives and things like that. We're just working with magnitudes at this point. Okay? So we said, remember, they've all got the same charge now. They're saying that S, P, and T all have the same charge. So for Q1 and Q2 in both calculations, we're just substituting in 3. So we say 3 times 10 to the power of negative 9 times 3 times 10 to the power of negative 9. Because Q1 is the charge on S, which is 3 times 10 to the negative 9, and Q2 is the charge on P, which is also 3 times 10 to the negative 9. Like I said, if you look in your description here, they all have the same charge. And now we say divided by, and the distance is given on the graph as 0.1 meters squared. And again, we're lucky because they've given it to us in our SI unit, which is meters. You need to be very careful. If they give it to you in kilometers or something else, you need to convert to meters. Otherwise, everything will be wrong. And so once we've done our final calculation for this, we know that the electrostatic force of S on P is equal to 8.1 times 10 to the negative 6 newtons. Okay? Okay, cool, perfect. Now you're going to do the exact same calculation, but you're going to do it for T and P. So now we're doing this side. Okay, so our constant stays the same. The charge on T and P are identical to the charges on S and P, so I don't have to change these values, but I do have to change the distance between them because the distance as stipulated on my graph is different. So now instead I substitute in 0.3 squared, okay? And once you've plugged that in, you get a net value for TP, or electrostatic force between T and P, of 9 times 10 to the power of -7 newtons. Okay, again, remember it's electrostatic force, so our unit is newtons. Okay, and now we go and we draw the same Cartesian plane, but with the information that we've just calculated. So we go and we draw and we say, so the electrostatic force that we calculated for P and T was 9 times 10 to the -7 newtons. And the electrostatic force that we calculated for S and P was 8.1 times 10 to the -6. And now, like I said, when you've got something like this, we're using the principles of Pythagoras. So we do this, and we do this. And this is the F net that we're calculating. This is F net. Okay, it's a 90-degree triangle. And you know that your formula for Pythagoras goes as follows. If we're doing it in terms of what we've labeled on our triangle, we say F net squared is equal to the force between S and P squared plus the force between T and P squared. Okay, so you substitute in your TP value over here, which is your 9 times 10 to the -7, and you substitute in your S&P value over here, which is 8.1 times 10 to the -6. And once you've squared them, you add them together, you square root them, because you need to get rid of the squared at the top here, and F net is equal to 8.15 times 10 to the -6 newtons. Okay, so quite a lot of brain power for this one, but you can also see that it's for 5 marks. So that does tell you that it's going to be quite a lot of work. Okay, now we move on to 7.5. Okay, 7.5. The net electric field at the origin due to charges S and T. Okay, so again, you need to go to your formula sheet, and you need to remember that your formula for electric field is E is equal to force over charge. And they're specifically asking for the electric field due to S and T. Okay, so due to S and T. Okay, so that means you're going to substitute in the net electric force, the net electrostatic force that you calculated in number one, because that was our hypotenuse side. So it'll be between S and T. So you calculated that value was 8.15 times 10 to the negative 6. And you divide it by Q, or charge. And the charge on all of them is negative 3 times 10 to the negative 9. So we can just substitute in the magnitude, because once again, they're only asking for magnitude. So we say divided by 3 times 10 to the negative 9. You plug that into your calculator and you get an answer of 2.72 times 10 to the power of 3. And then again, your unit is extremely important. And your unit for field or electric field is newtons per coulomb. Okay, perfect. Now we have a look at 7.6. One of the charged spheres, P and T, experienced a very small increase in mass after it was charged initially. Okay? Which sphere, P or T, experienced this very small increase in mass? Okay? So what they're saying is they're basically asking you to go back to the initial or the start, and they say that these spheres were all neutral, okay, which means they had no charge on them. And then they were given charges. Okay, P was given a charge of negative 15 times 10 to the negative 9 coulombs, and T was given a charge of positive 2 times 10 to the negative 9 coulombs. Okay, and so the sphere, remember that electrons weigh something, so do protons, but electrons weigh something. And if you go have a look on your formula sheet, it tells you that the mass of an electron is equal to negative 1.6 times 10 to the negative 19. That's the mass of an electron. So for this question, I would say that because P has got a more negative charge than T, P probably experiences a larger increase in mass, because remember, when you're adding, it's going to be basically, you won't be able to tell this change in mass from a scale, because this change is too small. Remember, the mass of an electron is tiny. It's tiny, tiny, tiny. But because our P sphere is being more negatively charged, it will experience a greater change in mass, even though you won't be able to perceive that change on a scale, right? You know mathematically through calculations that there will be a small change in mass of sphere P. And that's because we have added electrons onto that sphere. And that electron, or those electrons, have mass. Okay, again, this might be another formula that okay, no, this formula is definitely on your formula sheet, so you don't have to worry about that. But you'll see that so the question says which sphere, P or T, experienced this very small increase in mass. You can say P or T. The answer of P or T is correct. I'm going to stick with P because P is more negatively charged. And so my assumption is that there's going to be a more evident change in or increase in mass with P, because I've added more electrons to P than I have to T. And remember, the mass of an electron and a proton are identical. Okay, so if a proton or if an electron weighs 1.6 times 10 to the negative 19, so does a proton. Okay, but I'm going to say P. I'm going to say that sphere P experiences a small increase in mass, and now they want you to calculate this increase in mass on the sphere, and this is where that formula comes into play. And the formula goes as follows: number of electrons is equal to charge over the mass of an electron, or the charge on an electron, sorry. So this is charge on the electron. So number of electrons is equal to the charge of your object divided by the charge on an electron. So you know that the charge of the sphere initially, after it was changed for P, was negative 15 times 10 to the negative 9 divided by the charge on an electron, which on your formula sheet says negative 1.6 times 10 to the negative 19. You plug that into your calculator, and now you know how many electrons were added to your sphere. So 9.38 times 10 to the 10 is the number of electrons on sphere P. Okay? And now we say, okay, so now what is the mass gained? So I think I misspoke earlier. I said that the mass of an electron is negative 1.6 times 10 to the negative 19. That was incorrect. Negative 1.6 times 10 to the negative 19 is the charge of an electron, not the mass of an electron. But the mass of an electron is also on your formula sheet. So now you go and you say, okay, well, 9.38 times 10 to the power of 10 is the number of electrons that were added to sphere P. So there's another formula, and this formula says that mass or total mass gained equals the number of electrons, which is what you just calculated, multiplied by the mass of an electron. So the number of electrons that you just calculated was 9.38 times 10 to the power of 10. And then this is where the mistake came in from me, right? What I said earlier was the charge, it wasn't the mass. But on your formula sheet, it does say that the mass of an electron is 9.11 times 10 to the negative 31. You plug that into your calculator and you get 8.55 times 10 to the negative 20 kilograms. And that's how much mass was added to sphere P as a result of giving it a negative charge. Okay, and like I said, this number, it's so small. Can you see it's times 10 to the negative 20? It's tiny, it's minute. You would never detect this on a normal scale. So it's an imperceivable increase in mass. But as I said, you know, due to calculations, that electrons do have mass and they will affect the overall mass of the object that you're adding them to or putting them on. Okay, I think we leave that one there. And now we move on to question 8. Okay, question 8. The battery in the circuit diagram below has an EMF of 12 volts and an internal resistance of 0.5 ohms. Resistor R has an unknown resistance. Okay, so 8.1. What is the meaning of the following statement? The EMF of the battery is 12 volts. So what does that statement mean? Okay, that statement means that the battery is able to supply 12 joules per coulomb to the circuit. Okay? Or it means that the greatest potential difference that can be generated by the battery is 12 volts. Okay? The total amount of electric energy supplied by the battery per coulomb unit charge is 12 joules. Any one of those. Okay? It basically is just saying that 12 volts is the maximum amount of potential energy or voltage that can be supplied to the circuit by the battery. Okay? No more. It's the maximum amount of voltage that can be supplied. That's basically what it means. Okay? Now we move on. The reading on the ammeter is 2 amperes. So 2 amperes on this one. My suggestion is always that when you've got electricity or anything like this, if they give you additional information in the writing, you should add it to your diagram just to make it easier for your brain. Okay, and now it says calculate the 8.2.1, the reading on the voltmeter. Okay, and if you've done these questions before, you know that the most generally used formula for a circuit where we're taking internal resistance into consideration is EMF is equal to current multiplied by resistance, or the total resistance of the circuit, plus the internal resistance. So here our EMF, as it said, is 12. It told us that our current is 2. We don't have R, but we do have internal resistance, which is small r. It's this value over here, small r. And we can calculate resistance. We can calculate the resistance of resistor R here. So we substitute that into our calculator and we get a value of 5.5 ohms. Okay, but they weren't asking for the resistance of resistor R, they were asking for the reading on the voltmeter. Okay, so what do we do now? We say, well, according to Ohm's law, V is equal to I times R. And we know we're looking for V. V is what we're looking for. We want to know what is the voltage running through R. So we say, okay, well, we know that the current is 2. We've just calculated that the resistance is 5.5. So that means that there are 11 volts running through resistor R. And that's your answer to 8.2.1. And then, because I've chosen to do it this way, my next question is super easy. Because now the next question is, what is the resistance of resistor R? And you've already calculated it. Here it is. Okay? So super easy, that one. Not too bad. Okay? Then 8.3, it says, how does this change affect the reading on the voltmeter? So, they're saying no. They're saying that switch S is now closed. So I close the switch. And it's saying, how does this change affect the reading on the voltmeter? Choose from either increase, decrease, or remain the same. And you need to explain your answer. Okay. Well, the first thing that we know is that if you add this original circuit when switch S is open is a series circuit. Okay. Then when I close this switch and make this additional resistor part of my circuit, I'm adding a resistor. but I'm not adding a resistor in series, I'm adding a resistor in parallel. And you always know that total resistance in a parallel circuit will be less than the total resistance of the same resistors in series. So we know now that when we add this resistor, we are decreasing the total resistance of the circuit. Okay? And when you decrease total resistance, it means that you are decreasing your external potential difference. So your answer to this question is by closing the switch, I'm decreasing my total resistance because I'm adding this resistor in parallel now and not in series anymore. And by decreasing the total resistance, I am decreasing the reading on the voltmeter. Because remember, V is equal to I times R. Okay? And according to this formula, voltage is directly proportional to resistance. Okay? So that means by decreasing resistance, I'm decreasing voltage. Because what happens to the one happens to the other. Directly proportional means that if one increases, the other increases. Or if one decreases, the other decreases. Okay, perfect. Now we move on to question 9. So, learners perform an experiment to determine the EMF and the internal resistance of a battery using the circuit below. So here's your circuit diagram. It says that the learners use their recorded readings of current and resistance together with the equation R is equal to, so resistance is equal to EMF over current minus internal resistance. Okay, so you can see that this formula kind of looks like the formula of a straight line graph. Kind of, not exactly. R is equal to E over I minus R. And the formula for a straight line graph is y is equal to mx plus c. Okay, so very similar. So in this scenario, R is our y value or our dependent variable. M is our gradient, which isn't got anything there, so assume it's 1. Our x is, which on our graph has been drawn as 1 over current. And our minus internal resistance is our y-intercept, because plus c is our y-intercept. So the first question says to us, which variable has to be kept constant in the experiment? Okay, with electricity questions, the variable that needs to be kept constant when you're looking at these things is almost always temperature. And that's because temperature and resistance are synonymous. They're very closely related. Okay, because as temperature increases, so does resistance. So in order for your results not to be biased or incorrect or anything like that, your resistance can't be affected. Okay? And the only way we can make sure that our resistance isn't being affected by additional variables is if we keep our temperature constant. Okay. The next question says, write down the value of the internal resistance of the cell. Remember, I just told you, according to our straight line formula, internal resistance is our C, our plus C value, or our y-intercept. So all you have to do is you have to go and find your y-intercept on the graph. Okay? So here, if you go and you have a look, this is -5, so you go, this is 1 block. This is 2 blocks. This is 3 blocks. Okay? And yes, it's on the negative side, but you don't have to report it like that. So here is your y-intercept. So small r is therefore equal to 3 ohms. Because according to our straight line graph formula, negative r corresponds with the y-intercept, which when we read it off of the graph is 3 ohms. Like I said, don't worry about the negative. You can just report it as 3 ohms. Okay? Perfect. And then the next question says, calculate the EMF of the battery. So once again, and as I said, your standard formula for when you're dealing with internal resistance is EMF is equal to I times total resistance plus internal resistance. So in this scenario, EMF is what we're looking for. Okay, so we're going to need to go and find a point on the graph that we can substitute in here. We've got R. We know that R is 3 because we just got it off the graph. But now you got to go and you got to choose a random point on the graph, whichever one you want to, and you need to get a value for current and you need to get a value for resistance. So I'm going to use this last one here. I'm going to use this point over here. So from this point, I can see that my value for resistance is 11. Okay, and my value for current is 2. But remember, this is 1 over current, so it's 1 over I. I don't want 1 over I just want I. So I take my 2 and I say 1 over 2, and I substitute this value in as my current. Oh, I've swapped them around. Sorry. Wait, it's just written that in the wrong place. So my half is my current, and then, sorry, this was supposed to be substituted in here by R, my resistance, because this value, my Y value is resistance, and my X value is 1 over current. So you take your value for current, and you say 1 over what you get on the graph to get what needs to be substituted in here, which is 0.5. I apologize for that small mistake. And then we go and we substitute in 3 for R. And you put that in your calculator, and what do you get? You get 7 volts. Pretty straightforward. Okay. Not too bad. Okay. I think we can move on. Now we move to question 10. Okay, this is for an alternating current generator. So it says, in the simplified AC generator or alternating current generator, the coil is rotated clockwise. Okay, so now they say, first question, in which direction does the induced current flow in the coil? So it's very important to remember that when we're dealing with alternating current, you need to use Fleming's right-hand rule. Okay, so the right-hand rule is used for alternating current. So when we're trying to determine which direction is the current moving in, what direction is the motion moving in, anything like that. Okay, but you need to understand that this right-hand rule can only help you to get an instantaneous flow of current direction, because in alternating current, the current is constantly changing direction. That's why it's called alternating current. Okay, it's constantly changing direction. First it's going one way, then it's going the other way, then it's going that one way, then it's going the other way. It's constantly changing. Okay, but in direct current circuits, it's much easier to determine which way the current is flowing, because direct current circuits or direct current circuits or systems follow the conventional flow notion, which says that current flows from positive to negative, out of the positive terminal of the battery into the negative. And you know that when you draw a cell, in your circuit, the long side is the positive side and the short side, because you draw a cell like this. A cell is like a battery, right? So that's a battery, that's a cell in a circuit. And the long side is the positive side, and the short side is the negative side. So trying to determine which way current is flowing in a direct circuit is pretty easy if you know which terminal is positive and which is negative. Because with direct current, it always flows out of the positive and into the negative. So out of the positive and into the negative. This is not true for alternating current. Okay, alternating current, it's constantly changing. So you can only kind of determine the direction from an instantaneous point of view. And we always use the Fleming's right-hand rule for alternating current, okay? So it's a bit difficult for me to describe to you here how you're going to do this, but when you're trying to determine the direction of the induced flow, you put your hand out like this. Your pointing finger, you must put your hand in the shape that it's in the picture, and you point your pointing finger in the direction of the magnetic field. Remember, magnetic field always goes from north to south. It goes out of the north and into the south. So your magnetic field is pointing to the left, okay, because it's going from north to south, okay? Then we're trying to determine direction of current, right? But first we need to make sure our thumb is positioned in the thrust or the motion. They're telling you that this coil is rotating clockwise. So it's rotating that way, which means the motion, they're focusing on this side of the coil. They want to know, is it moving from Y to X or X to Y? And if this thing is rotating clockwise, it means that this side is moving upwards. The motion is moving upwards as this thing rotates clockwise. So your pointing finger faces from north to south. Your thumb points upwards because side YX is moving upwards as this thing rotates clockwise. And what this means is that current is going in the direction of your middle finger, where your middle finger is pointing. And that means that current is flowing from Y to X. Current is flowing from Y to X. Okay. Now, the next question says, on which principle or law is the working of this generator based? That's a pretty easy question. It's based on Faraday's law of it's based on Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction. Okay? You can just say one. You can just say Faraday's law, or you can say electromagnetic induction. You don't have to write both. Just thought I'd include both for sake of completion. Okay. And then 10.1.3 says, state the energy conversion that takes place while the generator is in operation. So they're saying, what type of energy is being converted into what type of energy in this scenario? Okay, and the answer is that movement or kinetic or mechanical energy, because as this thing is rotating, it's creating an electrical current, a flow of electrical current. So what is the energy conversion taking place? Energy is being converted from mechanical or kinetic energy into electrical. So mechanical or kinetic energy is being converted into electrical energy because the movement of this coil, the clockwise rotation of this coil within this magnetic field is causing electrical energy or the flow of electrical energy in these wires. Okay. Next question, 10.2. The voltage output for an AC generator is shown below. 10.2.1, write down the maximum or peak output voltage of the generator. So this is easy. Okay, where's the peak on this graph? Where's the maximum point on this graph? This is your peak. This is the highest point on your graph. So 10.2.1, your answer is 340 volts. It's the peak on your graph. It's not a trick question. Okay? 10.2.2, so we first say a stove is connected to the generator above and delivers an average power of 1,600 watts. 10.2.2, calculate the RMS voltage delivered to the stove. Okay, so we say, now you again, if you've got your formula sheet next to you, you'll immediately see a formula that has got voltage RMS, VRMS. And the formula goes as follows. You can see it's only for 3 marks. It's not going to be difficult. So it's going to be VRMS, this is on your formula sheet, is equal to Vmax, which is what you've just stipulated in the first part of the question, divided by the square root of 2. Super, super easy. So VRMS is what they're asking for, right? The RMS voltage is equal to Vmax, which we said is 340 over the square root of 2. And when you plug that into your calculator, you'll see that VRMS is equal to 240,42 volts. Simple, straightforward. Okay? The next question, 10.2.3, asks you to calculate the resistance of the stove. Okay? Now, there's a formula, they've given you power, you've calculated VRMS, and you want to know resistance. So you're going to go to your formula sheet, and you're going to see that there is a formula that says P average, otherwise known as the average power, which is what they've given you. They've given you average power, is equal to VRMS squared